I don't know if this has anything to do with what we're doing today, but see if I can start with. It is fluids, of course. Wake anyone up. Dolphins, I guess. Huh? Well, I guess I said that there wasn't really, well, it's fluid mechanics, but nothing so much about today. But I guess that's not quite true. When you look at these things, you look at the motion of the folks being driven by the jets of water, which is kind of an external flow. But the issue of being able to get water to the person and then a jet from that person is something that relates to pipe flow. Right? The supply of fluid to the individuals is along this umbilical cord that's there, and requires that to drive flow along there, you have to counter these losses that you have as you go along it. And so that's, I suppose, the connection between this and what we'll talk about today. And it looks like the driving the drivers for these things, I'm not sure whether they look almost like Sea-Doos, right, that are driving these. I suppose you could imagine that the basic characteristics of a Sea-Doo that take in water and squirt it out via pump could also be the supply for the bottom end of this pipe, the umbilical that goes to the person. And the only thing that's different between these guys and, well, it looks like guys or gals here is that they have this extra stabilizing flows from their hands, which are just two small hoses and outlets which allow them to maneuver a little bit as well. And so the connection, I suppose, is with our idea of the energy equation and how fluid flowing from a pump into an outlet will suffer losses, and those losses will be of two kinds, as we talked about last time, and that is that they could be major losses or minor losses. So that's kind of what we'll talk about today. And I want to veer a little bit off our scheduled plan today to do some slightly different things. We did talk last time about Bernoulliing the energy equation, and that's basically what we're dealing with. We did talk about the Moody chart, and so maybe we'll recap that. But and we've talked a little bit about minor losses and entry losses. But what I wanted to do, maybe rather than leave it into week 11, is talk about how we might solve some different problems using the energy equation with the head losses factored into it. So by way of summary, we know that if we're looking at flows in a system, then we can evaluate things in some way, and this is probably the simplest way that we can do it, between an inlet and an outlet. And you've seen this equation many times. But you could imagine that we could also define the fact that at different locations in the system, we would have losses within the pipe at locations 1, 2, 3, and 4. I know it doesn't match up with these numbers here. A pump within the system that adds or subtracts head. And if we want to solve that relationship, then what we have to do is we write Bernoulli in our normal way with the elevation, pressure, and velocity terms between 2 points. The pump addition to the system and equal to the downstream behavior wherever we write it. Again, is the sum of those individual terms, P2. And as we said last time, with the sum of the head losses, which are major. And we made the case last time that this head loss should be something like a friction factor, which is a bit like an Euler number, at least for pipes, length to diameter ratio of the pipe, and the velocity squared term, the inertial term, written for whatever the velocity is in the pipe, not necessarily at locations 1 or 2, and that the minor losses are for things like bends, and typically those minor losses are defined in terms of some loss coefficient, which is just a non-dimensional number, multiplied by v squared over 2g. So that's the basic relationship that we had, and we said also that we know that the head into the pump is equal to the power of the pump in terms of watts, joules per second, Newton meters per second, divided by, could write it different ways. We could write it as unit weight times the volumetric flow rate, and we could also write it as gravity times the mass flow rate. Because mass flow rate is volume flow rate times rho, density, right? So they're equivalent. And these are positive for a pump, and negative for a turbine. So that's kind of a fundamental relationship for us. And so in this, if we were doing this, then we would have loss factors for each of these minor losses within the system. And so if within our system we are able to define those, then we would use this expression, and all this would be that the sum of head losses which are minor would be equal to whatever the head loss KL1 was. And if in this is a single pipe of the same diameter, the velocities in all of these components has to be the same by continuity. So we could write them individually as this. Where these are the velocities actually in the fitting, either a bend around a pipe, or could be a valve in a pipe, or some kind of fitting that makes the bend in the pipe that has some roughness in it that gives you an extra loss, and that these would all be, I guess, however many of these there are. So we add these together. And so these would just go into this expression. And notably, I suppose, for us, the term that they're multiplied by and the term that the major losses are multiplied by become something that can be taken out of a bracket. And so if, for instance, the elevations were the same upstream and downstream, the pressures driving, well, if the elevations were different but the pressures were the same, so if this was just a top of a tank and this was also the top of a tank, then in this expression the pressures would be 0 because they're atmospheric if you do them between 1 and 2. The magnitudes of the elevations, I guess, would be finite, and this magnitude here would be Z1 to this point here, and this would be 0, and so we'd be left with this, and this would go to 0. Because the velocity in and the velocity out, if they're the same diameter pipe, so if we have same diameter pipe, then V1 equals V2, and in which case these two terms go to 0. And then if there's no pump, then we don't have to worry about it. And so if we say there's no pump, then let's put this to 0. And in this particular case, C1 is going to be equal to the sum of the major losses and the sum of the minor losses. And so implicit in that is that we can define these in terms of, for this, it's going to be a friction factor, length over diameter, and this term v squared over 2g in the pipe. And added to that would be the magnitudes of whatever KL1 plus KL2. I'm just doing this conveniently to put it in the same color. Etc. And so that can be simplified just as equal to the sum of those individual components, friction factor length over diameter plus KL1 plus KL2, etc., all multiplied by the velocity, the inertial term, v squared over 2g term. And so in that, the only thing that we know this, and so the only term that we don't know in this is going to be this. And so long as we can define these individual components, then we're able to solve for flows in systems of pipes, and with various degrees of complexity, I guess, that have these individual fittings in them. So we'll talk a little bit later today maybe about what these losses might be, but I think the only thing to realize is that they exist and can be quantified in terms of tables that say something about what those losses should be. Again, this is the expression that would define that particular behavior. And so if you have a pipe of a particular kind with a bend of a particular angle, and depending on what the material is that it's made of, in terms of what the individual internal roughness might be, then we can define magnitudes of this coefficient multiplied through by this v squared over 2g term. And so kind of implicit in this is, as we mentioned last time, is that probably we're basically assuming that the behavior within these fittings, whether it's a bend or a junction or individual valves, which might look like this, right, if it flows through this, is that the flow within these is turbulent. And the reason that we can suppose that is that we have a single constant magnitude of this typically, which doesn't vary with Reynolds number. And so in terms of where we are on the Moody chart, then it's a location where the Moody chart lines are horizontal, not the ones on the left-hand side. So it's not so important to know exactly what these losses are, because we know we can always figure out what they would be just by looking up a reference text. But perhaps more useful is to understand exactly how we might use them. So what I wanted to do today was to maybe spend some time going through something that comes in kind of week 11, but is probably worthwhile looking at now, and that is to talk about how we can do these kinds of calculations for a variety of different ordered ways of doing it. And so the ordered ways of doing it are that we can do this, draw a line under here. So you can imagine that we might want to look at flows in, basically flow in pipes, which is what we're talking about anyway. And we can always use that expression that we just defined, but we can maybe apply a formalism to what we solve for. So you can imagine that we might want to solve for the losses in a system, or we might want to figure out how fast the flow is within a system, like in the jet lavs we just saw on the video. We'd like to know what the velocity is out of those, given the pump in the system and the head losses along the pipe, what the velocity can be that would lift us out of the water. Or you might want to know what the velocity needs to be to lift a person, and to figure out what the dimensioning of the pipes would be and the pumps that would allow you to get there. And so you can imagine that we might want to solve for those basic three things. So the basic three things might be geometry, and so for geometry, that might be the diameter of the pipe, it might be the length of the pipe, it might be how rough that pipe is. We talked about this on the Moody charts. We might want to solve for the flow rate. And so that would be velocity, or I suppose it could be Q, the volume flow rate, or the velocity out of the system, or the pressure drop. And so those three things, and pressure drop would be our head loss, or I guess it would be our pressure drop from upstream to downstream. So those are the three things that we might want to solve for. And so the formalism that's used in the book and that we'll use as well, is that these are defined into what are called so-called type 1, 2, and 3 problems. Type 1, type 2, and type 3. And the only thing that makes them different is that in type 1 we solve for this, so we want to determine this. So this is what we want to know. And so we would need to know these other components to be able to do that. In type 2 problems, what we want to determine is flow rate. In type 3, we want to figure out the geometry. And in each case, you'd need to know the other components to be able to solve for that. And so today what I wanted to do just was to talk about each of these first two anyway. We've kind of talked about the first one, but let's go through an example just to make sure you understand it. We'll leave the third one, which is more complicated, dimensioning the pipes that you need to use, for another time in week 11, next week. And so that's what we plan to do today. And so let's figure out, I'm going to move just to a clean sheet that I just made that actually has a Moody chart on it. So you don't have this, but you don't necessarily need that right now. And so let's figure out let's just do a problem, and not one that's in the book, but one that we can define ourselves. So if we look at this type 1 problem. So this is to define either the head loss or the change in pressure, bless you, which are kind of the same things, right? If you think of the geometry that we've talked about, then we have a pipe of some length and some diameter. And I'm going to have to contrive this problem. So it has a diameter, it has a length of pipe that we have. We know that over its length we have a head loss, or a pressure drop. And of course that pressure drop, delta P, is equal to head loss divided by unit weight in this geometry, right? So that's physically what it represents. Water comes through here at some velocity, which we have to prescribe. And I suppose we have material properties, which would be viscosity and density, which control behavior. And so to be able to solve for either one of these two things, well, they're the same thing, right? For this, we need to know all these other properties. And so what we need to realize is that our way to solve this is always going to be dependent. This one is the easiest one. And it's the easiest one because we're solving for the head loss where all the other properties are defined. So in other words, the velocity is defined. And so in the case where velocity is defined, we uniquely know what the Reynolds number is. And so we uniquely know, given what our pipe is, exactly what the friction factor would be. And so we can solve it, if you like, in two regimes. And we know there are two regimes. One is where there's a laminar flow, and the other one is where it develops into turbulent. And the characteristics are that in the laminar regime, we know that this line is equal to 64 over Reynolds number, which is the friction factor. And once we get beyond that, we know that if it's wholly turbulent, then the friction factor is constant given the magnitude of the roughness. And so we can solve this in two ways. So I suppose we can solve it in laminar or turbulent. Or transitional for that matter, I guess. So we have to figure out what our properties would be. So we know that we need to know something about the Reynolds number. And that is equal to density, velocity, diameter of the pipe divided through by viscosity. So typical numbers for these for water would be something like density we know. Make this bigger, I suppose, right? And viscosity is of the order of 1.2 times 10 to the minus 3 Pascal seconds, but let's not worry too much about that. Something of this order. So we have that. And so if you look at the magnitudes that we'd have for this, it's probably easiest for us in contriving a problem to look at it in terms of these two separate variables, slightly separate variables. Because this is a velocity, a diameter of the pipe, I don't know what a reasonable diameter of a pipe might be, 0.1 of a meter, 10 centimeters, right? So that's quite a big pipe. So let's put diameter as 10 to the minus 1 meters. And density is 10 to the 3 kilograms per meter cubed. And viscosity is 10 to the minus 3 Pascal seconds. And so this right-hand term that multiplies velocity is something like velocity multiplied by, this is 10 to the 6, 10 to the 5, times 10 to the 5. And it will have units. I'm not going to work out what those units are. Certainly if you use meters per second for this, then the units will work out to be just fine. They'll cancel out. Because Pascal is a Newton per meter squared, and a Newton is 1 kilogram meter per second squared. The force needed to give a kilogram an acceleration of 1 meter per second squared. So this will work out. So I guess this must be in units of seconds per meter. Because when you multiply it by meters per second, you get a non-dimensional number. So you could probably explore that yourself, but certainly that has to be the case here. And so, to be able to probe these two regimes, laminar versus turbulent, we're going to make the case that turbulent starts at 2000, Reynolds number of 2000. This is here. And so to be laminar, we need to be less than that. So this number needs to be less than that. So to be 1,000, the velocity has to be 10 to the minus 2, right? So for laminar, and so if that's the case, then we can certainly calculate the head loss, which is going to be a friction factor, length over diameter, v squared over 2g. And so for sure we can calculate the friction factor. By definition, if Reynolds number here is going to be 10 to the 3, then we can do it this in two ways. We could either figure out what our friction factor is from this, which is 0.062, something like that, right? So this is equal to 0.062, and we know if length is equal to 1 meter, we know this is 1 meter, we know this is 10 to the minus 1. We know the velocity is equal to 10 to the minus 2. And we have everything we need to calculate the head loss. And we could figure out what that magnitude is. I guess we could probably... so that's one way to do it. So I guess if we did that, what do we get? This is equal to 0.062. This is equal to 1 divided by 0.1, which is 10. 10 to the minus 2 squared is 10 to the minus 4. The only painful one is 2g, so 2g is basically 20, right, meters per second squared. So divided by... And so what's that going to be roughly? This is 10 to the minus 3. 1 over, so 1 over 20 is 1 over 2 is 0.5, 1 over 20 is 0.05. Times 10 to the minus 3, and it's in meters, and that'll be whatever that is. So I'm not going to work that out, but we can do that straightforwardly. If we knew that we wanted it to be turbulent, then instead of being this, if it's turbulent, we go through the same thing. We know that, well, a velocity of 1 meter a second will give us turbulent behavior. That would give us a Reynolds number of what? So if this is now 1 meter a second, the Reynolds number would be 10 to the 5. The magnitude of the friction factor for 10 to the 5 depends now on the kind of pipe you have. So this is 10 to the 5, and so we'll be on this trajectory. If it's a smooth pipe, we'll be at this point here, in which case our friction factor would be equal to 0.15, 6, 7, 0.175. So if it's smooth, it's 175, I say. Yeah, 175. And if it has some roughness of, I don't know what the order of magnitude roughness coefficients are, let's choose 1 over 1,000. So that means that the pipe, as it goes downstream, has this roughness on it, and this roughness has an amplitude of epsilon, and epsilon divided by the diameter of the pipe is some other number. And if that's the case here, then all it means is that we go further up to this particular point here, which is for this one here, and then across. And it says, not surprisingly, that if you have a rough pipe rather than a smooth pipe, the friction factor is larger, 0.022, I suppose. Which means if you calculate the head loss from either one of these, just directly by using the friction factor, length of the pipe, diameter of the pipe, and the velocity in the pipe which we have defined, which is now a larger number, we can calculate what the head loss would be in the system. So it's no different from that. So this type 1 behavior is the easiest. So going back to our chart maybe that we wrote down before. So this type 1 behavior is kind of the easiest because we know the velocity, so immediately we can calculate the Reynolds number. And if we can calculate the Reynolds number, we know exactly where we are on the Moody chart, and we can calculate our friction factor loss coefficient directly without really iterating, because we have it. And if we have that, then we have everything we need to be able to calculate the remainder. The less easy ones, as I suppose I alluded to this before, is that the degree of difficulty is in going down in this direction. Because you can't, if you're trying to determine the velocity, clearly you don't know the velocity in the first place, and therefore you can't calculate the Reynolds number directly. And so that means that you probably have to iterate in this, and then this gets slightly more complicated because neither do you know the velocity. You might want to prescribe a velocity, but you don't know what size pipe. And so if the Reynolds number includes the diameter of the pipe, which it does, then you don't know the Reynolds number in either of these two. So in these two, typically, if a diameter of the pipe means you don't know the Reynolds number, and the velocity in the pipe means you don't know the Reynolds number either, and therefore you have to iterate on them. And so if that's the case, then we can go back to our situation here, I suppose. I suppose what I could do is I could remove this part. So you have this is all recorded, so I don't really need this. Oh, maybe I do actually, because I might actually want to do those calculations in a moment for other reasons. All right, so let's just do it. Let's go through the same idea as before, and let's do it for our so-called type 2 behavior. So here we have a system which is probably going to be similar to the other one, I guess. Do it this way. I'm trying to draw two reservoirs with a pipe between them. And with some difference in elevation between them. And we can do what we did before, which is write Bernoulli equation between 2 points. And figure out exactly what we do and don't know. We won't put a pump in there, just to make life easy, because most of these terms we'll want to get rid of. It won't be very different from our previous case. These are 2's, of course. And we're going to ignore the bend losses, just do the major head losses, which are only going to be in this piece of pipe, which is going to be the same pipe we had before, which is the same length and the same diameter as before. And we can write Bernoulli between these 2 points here. So pressures go away if we take the surfaces. For the same reasons as before, the velocities in these tanks also go away because they're 0. There will be a velocity in this pipe, which will be friction factor, length over diameter, velocity squared in the pipe over 2g. And the only terms we have relative to our datum, I guess you can choose your datum wherever you want. If you choose it here at z equals 0, then this ends up just being z1, and this goes to 0. So in other words, the head loss in the system has to equal z1 minus z2 in this particular case, right? So we have this from our geometry, and we need to be able to figure out exactly what the magnitudes of this are. And so the problem is that now we start off and we don't actually have a value of velocity to use. I suppose we could use one of the ones that we had previously to make sure that we're in the right regime. But essentially what we might want to do is to maybe, we could assume laminar. For instance. And if that's the case, then the only thing we don't know here is the velocity. We don't really know the magnitude of friction factor either, though, right? Because only in the special case where we know that we're turbulent and we have this geometry do we know that this has a single number, and that we could put that in straight away and solve for the velocity just by taking the square root of that resulting expression. If we're not there, though, then we don't actually know where we are on this curve. And so I guess we didn't do the calculations for this, but the head loss here is going to be actually a very small number. Is that right? Is that really 10 to the... Yeah, I guess for the laminar case it's a very, very small number. And we didn't really do the head loss for this one, although I suppose we could get a rough idea of it. So this is what? This term here was something like 10. This term here was 0.022. And this term here is 1 divided by 20. So this was 0.05. So the magnitude of this is 10 times this would be 0.5, and 2 times 0.5 would be 0.1, but with 0.001, something like that. And so that magnitude is going to give us turbulent flow. So I'm guessing actually, well, why don't we just choose a value of this of 1? I'm pretty sure it'll give us something that's turbulent. So if this is 1 meter, what do we end up getting out of this? We get out of this, if we assume it's laminar, then we know that the friction factor is equal to 64 over Reynolds number, which is equal to 64 over rho v d mu. And so we could substitute that into this expression where head loss is equal to 64 over rho v d mu times length over diameter times v squared over 2g. And so in the laminar case, we know that we're going to lose a velocity term and not much else, I guess. And we could rearrange this as the velocity is going to be equal to head loss, density, I guess d squared for these two, times 2g, divided by 64 times viscosity times length. And so immediately we could calculate the magnitude of this. Do we have, yeah, sure, why don't I do that? And so if those numbers are 1 meter, density is 10 to the 3, the diameter was 10 to the minus 1 meters squared, times 2 times 10, roughly, right? You can do the check on the units. Over 64 times 10 to the minus 3 times 1 meter. And order of magnitude of this is something like, this is 10 to the minus 2, this is 10 to the 3, so 10 to the minus 2 and 10 to the 3 are 10 to the 1, right? Times 10 to the 2 divided by 10 to the 3 is 10 to the 5, something like 10 to the 5 divided by 2 over 64 divided by 30, 32. Is that right? I don't know. Something. And it should be in meters per second, so the bottom line is that's a big number. It's a very big number. So take this as being roughly 100, so this is something of the order of 10 to the 3 meters a second. If we have 10 to the 3 meters a second, we can check that the Reynolds number is going to be equal to 10 to the 3, 10 to the 3, 10 to the minus 1, divided by viscosity. And this is going to be of the order of 10 to the 6, 10 to the 9, 10 to the 8. And so if it's 10 to the 8, well, we don't go here, then we'd be actually off the chart. And so we can't actually use it. Well, I guess we can. If we say that it's a rough system, so if we make that requirement, then 10 to the 7 and 10 to the 8 would be exactly the same friction factor, and they'd be equal to this magnitude here, going across here. And so actually in this case, if that's truly the case, and we solve this, we'd find out that the friction factor is equal to 0.02, and if the relative roughness is equal to 1,000th. And so now we don't know whether at this new friction factor, the friction factor we assumed before was probably different from that because it was varying with an assumed Reynolds number. We have to check now what the true velocity is going to be of the system. So we can't quite use this again, but we can use the expression in its slightly different form. So head loss is equal to friction factor L over D V squared over 2G. And we can change that so that we rearrange it in terms of the velocity. And so that will be the head loss, which we said was a meter, the diameter of the pipe times 2 times gravity divided by the friction factor and the length of the pipe has to equal V squared. And so if we get rid of V squared, we do that just by taking the square root of this. And so that's the point, that since we don't know the velocity in the first place, we have an initial guess, and we have to move to now refine that guess by having something that we now know. So what we now know is that this friction factor has to be 0.02. Is that right? I haven't missed a digit off, have I? No, 0.02. And so we can do that. So 1 meter multiplied by 0.1 meter times 2 times 10 divided by 0.02 and multiplied by a length square root should be something like, I'm not missing anything out, am I? So this is 0.1 times 10, which is 1, times 2 is 2. This is 1 meter. So 2 divided by 0.02 is 100, right? And so we have a velocity of 100 that we've calculated, 100 meters a second. And so what we should do probably is also check the Reynolds number once again. So this, our first calculation was a velocity of 1,000 from assuming that the losses were laminar, and it came out to be that magnitude. Square root, okay, yeah. It is square root 100. Okay, thank you. Equals 10 meters a second. Yeah, great. So this was based on an assumption that previously we thought it was 1,000, and now it's not, because the losses are actually larger, because it's turbulent. And so we think it's now 10 meters a second. So now we should check the Reynolds number. Reynolds number is velocity, density, diameter over viscosity, which will be 10 meters a second, 10 to the 3 kilograms per meter cubed, and 10 to the minus 1 meters, divided by 10 to the minus 3 Pascal seconds. And if we do that, it's 10 to the 6. I guess these two cancel out, right, on this side. So it's 10 to the 6, non-dimensional number. We go back up to here, 10 to the 6, and we find as if we go up to the same roughness value, we end up with exactly the same friction factor. And if we use the same friction factor and went back to do this calculation again with this, we'd find out that indeed, thank you, the velocity is equal to 10 meters a second. And so that's the iterative way of being able to do this. And so it's important that we kind of understand the difference between these two regimes, because it changes the way in which we might want to manipulate the data. If we know for sure that your laminar, you can solve in one step, because you can write this head loss equation, as we did, merely in terms directly of the velocity, without having to square root it. And the reason for that is that when you substitute in the value for the friction factor, it includes the Reynolds number, which includes the velocity, and these two, one of these velocities cancels out, and so you get rid of it and solve directly. And so if you know for sure it's laminar, then you can solve in one step to get the magnitude of the velocity. But typically you don't know that, or you might not know that unless you're told that. And if that's the case, then surely you could assume it's laminar to do the calculation, but then you should check to make sure that you're really in the right regime. And the only way you can do that is by checking that you are laminar, and you can do that by looking at the Reynolds number. And for laminar flow, the Reynolds number is less than something like 2,000. See it on this chart up here, this value here. 2 times 10 to the 3. So this is this distinction. And so if that's the case, then you need to know something about the roughness of the pipes. And I guess the important components of the roughness are to realize that this is the laminar relationship here, which is independent of roughness, right? There's no relationship that relates this to epsilon over d. But if you have rough pipes, then you have progressively rougher. So these are quite smooth to quite rough, increasing magnitudes of this ratio of epsilon over d. And the delimiting magnitude here is a smooth pipe on the outside. I can't draw a straight line through it because it's not a straight line, but it's almost a straight line. And that is that on this boundary here represents the behavior of smooth pipes. And so that's kind of a bit partway in between the turbulent regime and the laminar regime, in that there's never really a single magnitude of friction factor for a smooth pipe because it varies throughout the range. So it's a bit like a laminar pipe, but we don't have a neat closed form solution to say it's 64 over Reynolds number. It's some different number, and you have to take it off the graph. And so merely making the point that when you go through this, sometimes you have to iterate to get a solution if you're in this regime where we're in these so-called type 2 solutions that we've identified. So that's kind of where we are. So what we did today really was just explore these two. By far the easiest one is when you're given a velocity, which means that you know the Reynolds number, and therefore you can figure out directly from this relationship here exactly what the head loss is, because this is a function of velocity, which you know, and this is a function of velocity or not. It's a function of velocity in the for a smooth pipe or in the laminar regime, and so you can calculate it in one step altogether. And in the turbulent regime and for rough pipes, it's not a function of roughness at all, it's just a single number that you'd know anyway. So this type 1 thing is the easiest one to get. The next wrinkle on this is when you don't know what the velocity is. So one way to do it is to assume some condition. You could assume it's laminar, or you could assume it's turbulent. If you assume it's laminar, then you can use the method we did. So you just throw 64 over Re into this number here, which is what we've done. Because Reynolds number is a function of velocity, it knocks out one of these velocities here, and so it gives you head loss is a function of velocity. If you did it assuming turbulent flow, I guess you'd end up just having to square root it, so this is easier. And then once you've calculated what the velocity is for your first estimate, then you have to go back and check with the Reynolds number to make sure that it's the right magnitude. And so you have to, yeah.
I see now
Yep. Yep. So long as you, if you have a given roughness of the pipe, then it's a straightforward because you know F directly. And if you don't know the roughness of the pipe and need it smooth, then you don't. Then you probably have to iterate to get it along this surface here. So if it's turbulent, then you know exactly what the friction factor is if you know the roughness. If you don't know the roughness, or if it's a smooth pipe, then you'd have to use the Reynolds number and then pull a friction factor as we did off that graph to get it. That's all. 10-2. Okay, great. All right. Well, I'm pretty sure that we'll have the exams out on Monday and the scores over the weekend. We're right at the end of that now, and so that's gone. The reason for doing this today is that I know we're only giving you back your stuff now, but the next midterm is on the 7th, which is, I guess, a week Wednesday, and so it covers up to the material that we've talked about today, and you can read in as you wish to what we've talked about today and why we might have done it today. So.